Hi everyone, welcome to Practical Exploitation of Insecure Randomness. I guess introducing myself is a good start to any conference talk. Hi, I'm Nathaniel Latimer, aka Donut. I'm currently a senior security engineer working at a startup called Cruise, headquartered in San Francisco. I previously got my start doing security professionally at Dropbox, where I joined the application security team. There, I focused a lot of my energy in running Dropbox's bug bounty program on HackerOne. Speaking of which, if you haven't hacked on Dropbox before, definitely give it a go. They have a really permissive scope, pay well, and have one of the most competent AppSec teams out there. It's a rewarding experience that'll definitely leave you walking away having learned something. To continue on, as mentioned on the slide, I'm pretty nerd snipeable. If you find just the right thing to get my attention, you'll ruin any chance of me being productive for the whole day. Unfortunately, or rather fortunately for myself, a friend of mine had done just that. They reached out to me asking for some help on a Node application that they were pen testing. My friend showed me some code that looked similar to the above function. This was a gray box test, so they had access to source code as well. This function was used whenever a user wanted to recover access to their account. It would generate a random number using Math.random, multiply it by some constant, in this case 10,000, and then would send this code via SMS to the user. If the user would put this code in the next prompt, they'd be able to reset the password for the account and log in. Clearly, in an application like this, there are tons of other vectors that you'd rather explore first, like XSS on the front end, SSRF to attack internal services, CSRF to get the user to do actions on your behalf. Perhaps there's some sort of type juggling attack due to the loose and strict equality checking present in JavaScript, and tons of potential for IDORs and other business logic issues, especially around authentication and authorization. But my friend saw Math.random and said, "Hey, Donut, you busy?" And then I got to work. So if you're not familiar with Math.random, in most programming languages with this construct, Math.random is a random number generator that traditionally is not cryptographically secure. These functions tend to use operations with various levels of reversibility or guarantees to generate the next value in a sequence. To any good AppSec engineer, they'll correctly identify using Math.random in a cryptographically sensitive area as a vulnerability. However, we generally don't put a lot of credence to exploiting insecure randomness. Yes, it's bad. Yes, it undermines your cryptography, but in terms of practical exploitation, it's not really there. Especially when we look at the code in the previous slide. We took the raw randomness and ran a step function atop it. This is elided randomness, meaning a random value that has lost some or most of its information. Sure, it's not feasible to exploit without thousands and thousands or even millions of SMS codes, right? Well, as any good hunter or red teamer, I decided POC or GTFO. So the first thing I did was I wanted to learn a little bit more about, what I'm about to spend some time attacking. So I looked up Math.random in V8 and found this blog post back from December 17th of 2015 from the V8 group. If you're unaware, V8 is the JavaScript engine used in Chrome and in Node.js. So anyway, the whole point of the blog post was that they were going to change the way that Math.random works. So before, it used a function called multiply with carry, or MWC1616, which was pretty good, but they wanted to switch to a new function that underlied how Math.random worked, called XS128+, or XOR Shift 128+. Why did they want to move? Well, it turned out to be better in a number of different ways. One, it was a bit faster, required less memory. Two, it turned out that it was statistically better at being a random number generator, and it also gave them more values before a cycle occurred. Now, in the code, which we can see on the left, or in the blog post, there was some code which we can see on the left, This is how XOR Shift 128 Plus works. It's pretty small, and clearly the only pieces of memory we need to worry about are, something for the stack for the call into XOR Shift 128 Plus to track, function address, and then we also have state 0 and state 1. So they do a little bit of bitwise math, some XOR, and some bit shifting left and right, and then we add these numbers together. Or this is the next output for XOR Shift 128 Plus. The code on the right is the code actually from the V8 source code where they're calling into their internal implementation of XOR Shift 128. So I wanted to look up some prior work and see what has been done. Has somebody solved this problem already? It would give me a better idea of at least where to start. And if I got really lucky, somebody would have solved the problem already. So I found this on the Security Stack Exchange. Somebody had asked this question, and I was reading through some of the responses. So these really, really long and solid responses. But then I came across one of them from this individual whose name was Douglas Goddard. Now, Douglas had done an excellent job in his post. I absolutely loved it. He even linked to a longer blog post where he described his motivations for all the work that he did. So Douglas did this blog post on Medium called Hacking the JavaScript Library. And it turns out that back in 2016, the Powerball jackpot lottery had a massive, massive jackpot of $1.5 billion. And apparently this had generated so much interest in it, and everyone was talking about it, that the LA Times ended up releasing this game. It's like a little simulator, so you can learn how unlikely you are to ever win this lottery, just due to the amount of people buying tickets and the odds that are playing against you. Well, Douglas was interested in this for some reason and wanted to win. So this game didn't have any server-side components. It was all client-side and used Math.random to generate these values that you would play against. So what Douglas had done is he had wrote some code in Z3 that took the raw output from Math.randoms and then rebuilt the internal state 0 and state 1 values that we saw in the code prior. And this allowed him to predict future invocations of that code, of that function, so that he would know what the next value was, what the next numbers were for the Powerball jackpot lottery. So what does that Z3 code look like? Well, Douglas linked to a GitHub repository where he had some of the code in it. So this is symbolic execution of XS128+. We can kind of see that more or less the code has remained the same, if not just changed slightly. We see many of the same bitwise operations, and if you're clever, you'll notice that LSHR does refer to a right bit shifting, and you can see left bit shifting done. So I've been mentioning Z3 a fair bit, especially with the work that Douglas Goddard had done, but I hadn't really covered what Z3 is. So Z3 is a satisfiability solver. And keep in mind, I'm not an expert in it, and in fact, this was my first usage of Z3, so the explanation may lack a little bit of nuance. But satisfiability is this idea that you can take a number of statements or expressions that you wish for all of them to be true, and Z3, or at least in general satisfiability, attempts to determine if there's some set of inputs that satisfy all of those expressions. So it'll let you know whether or not two equations intersect, or if two sets or multiple sets of Boolean statements can all be true together. And Z3 in particular will determine that, and it'll also give you a set of inputs that makes all of those expressions true. So to demonstrate Z3, I pulled up a site called Wolfram Alpha here on the left. Wolfram Alpha is a website where you can pose it questions, say things like, what's the weather, or how large is the Earth? And you can even use these types of questions in mathematical expressions, and Wolfram Alpha will do its best to understand and solve the question that you had. So in this case, I asked it to solve for these three equations, which you can see it plotted out in the graph below. So we put an equation for a circle, a polynomial degree 3, and also a bound on x, saying x must be greater than 1. And you can see that it also produced a result which shows where all of these equations intersect. So on the right, we did the same in Z3. So this is using the Python bindings for Z3. We declare two variables. One is x, one's y. They're both real variables. And then we put the bounds using the solver.add method. So there's the first equation, second, and then the bounds on x at the end. So we can call check and determine whether or not this is satisfiable, i.e., is there a solution? And at the bottom, we call model, which will return a result, a set of inputs that makes all of these statements true. So it kind of seems like all I have to do is take XS 128 plus and just solve for it, right? I mean, I don't even have to write the code. Somebody had done this and put it on GitHub, right? That's wrong. That is definitely wrong. It turns out that there were a number of issues and things that have, like, the game had changed since that blog post was written back in 2016. The first of which is we're not dealing with Math.random. We're dealing with that elided randomness that I talked about prior. But this is Math.floor of Math.random times a constant. So funny enough, after I had done all this work and was looking at some, looking at different things to pull pictures and screenshots in for the slides, I did find somebody had written this comment in that thread I didn't notice before, but somebody was also asking about this, and they had this really awesome point right at the very end of their question. And they said, you know, would this allow for solving an implementation, or would this allow for solving an implementation that uses Math.random in an algorithm such as Math.floor of Math.random times a constant, or would it lose too much to be retrievable? And that was the question that I had on my mind as well. So, quick reminder, this is the code that we're dealing with. As I just said, Math.floor of Math.random times a constant, and we're definitely not getting all of the underlying information of the randomness anymore. So I want to add the concept of Math.floor to the Z3 code. I need it to know what Math.floor is. Unfortunately, and this is partly hinted by that LSHR function, Z3 does not understand Math.floor. It doesn't know how that works. It doesn't have a way to express that readily as far as I could tell. I tried to look this up and I didn't see anything. So I was kind of dead in the water there, but I needed to be able to express that so that Z3 would be able to solve for it. I should explain how this works really quick. So we do have this first function, or we have this first section here, which is the symbolically executed XS 128 plus. On the right, you see the code that came from the blog post, the V8 blog post, and you can see how similar the two calls, the two functions are. The next part, the first line there is the symbolic code where we're getting the value out of that XS 128 plus by adding the two state 0 and state 1 together. And at the bottom, we have this code that came directly out of the V8 source code, and I made a screenshot of it to share. So we can see it's still the same. And then we kind of get to this part that's Z3 specific, where we build this condition. And the generated value is the floating point value that comes from when you call Math.random, and you convert that into a 64-bit integer. First, we have to figure out how to work with floating point numbers. So as I mentioned, floating point numbers, or doubles for double floats, they have this internal representation. In this case, this is a double float as it's 64 bits. Each of those squares represents a bit. On the leftmost, we have the sign, which is represented as, for positive, negative. That's a single bit. We have 11 bits that are dedicated to a exponent. If you look at the math below, you'll see 2 raised to the exponent minus 1023, which corresponds to having the last 9 bits set. And that means that values that have more than the 9 bits set will be above 2, and then we'll have values less than that be below it. And then we have this last section of 52 bits, which is called the fractional amount, or also known as mantissa. And this part represents kind of like the fine-grained control that you have in floating point numbers. And it's kind of a complicated thing. You can see there's a sigma or summation of the different values. It's kind of a whole thing. But yeah, we have to work with this. It looks awful, right? Well, we can kind of cheat a bit. So we know Math.random only outputs values between 0 and almost 1. And so that means we can ignore the sign. We can drop it entirely because we know it's always going to be 0, which represents, or actually it might be 1, but basically we just know it's going to represent positive. And the exponent must be equal to 1023, which is true for most cases. There is a small edge case that I do handle. You'll see it in the code in the next slide, but it really isn't, it doesn't matter except for a very, very tiny edge case in how Z3 was solving. But anyway, we know that the exponent must be 1023. So then this means that we can more or less do a direct comparison of the fractional bits. So we can take those 52 bits and compare it with a different set of 52 bits and use this to do a bounds check that's similar to how Math.random works. So you can kind of see that here. I wrote some symbolic code that does this. So I call from double on these generated values. I add 1 so that we have kind of a range of a lower and an upper value that can fall in that range where Math.floor produces the same result. So we do this bitwise math with the mantissa so that we can just get the mantissas. And then you'll notice on the very left-hand side of the condition at the bottom, we are comparing that the calculated value is greater than or equal to the lower mantissa. And on the right, you can see that there's that edge case. That only happens if one of the values that you're producing, the expected ones, is at the very, very top of the range of values. So if I have a range of 0 to 10,000, that only comes into play when the value is 9999. That's just to handle that edge case. So the next problem I had was just kind of a quick one that was easy to get through. But in September 24th of 2018, so this is 2 years, over 2 years after that blog post was written by Douglas Goddard, VH actually changed how they produced values out of XS 128+. So if you remember, state 0 and state 1 were added together. But now it actually took state 0, shifted it over 12 bits, and then added this, bitwise ORed, this constant called k exponent bits, and that was the output. And you can see that they also, there's a bit cast to double, and they subtract 1 afterwards. So this was just a random change. I had to go and write into the symbolic code to fix, and that was pretty easy. So this last one was really annoying. So there was a bit of a hint of this on the original GitHub repository, but I had to really figure this one out more or less to get it working quite right. Turns out that the way Math.random works is not the way you think it would. So the way it actually works is you're in the JavaScript runtime. You invoke Math.random for the first time ever. Well, the inner random implementation in V8 checks that this first checks with the cache. It says, is the cache empty? And it'll get a true value because it's never been filled before. So then it will fill in the next 64 values. So this means that the internal XS 128+ code gets called 64 times in a row. And each one of those values gets pushed onto the cache. And then it calls to pop the top value off. So it does this and sends the values back to the runtime. But it does this it'll do this up to 64 times until the cache is empty again, and repeat this process. So this kind of complicates things because now values are coming out of order. So what actually is happening here is the red lines are representing the cache fill events where we actually have to populate the cache with some internal random values from XS 128+. So we have the first call that ran 0 is actually going to be the last value that Math.random returns before a cache fill event again. In fact, the first time you call Math.random, that random value was the 64th invocation of XS 128+. So what kind of implications does this have? Well, I'll get to that in a second, actually. I just want to show you really quick in V8, you can see These are this is the code that basically checks to see if that cache needs to be filled and actually fill the cache and then pop values off. So what are the implications? Well, we have to reverse the inputs. So if I get the values like 0.2, 0.5, 0.8, I have to reverse that to 0.8, 0.5, 0.2 before I process it. Otherwise, I'm doing excess 128 plus backwards, and that's not going to be easy to do. So we need to make sure that we have like the order right. However, if I have to collect a lot of values, then we can cross cache fill events. So that 64 number boundary, if I have to use more than 64 values, or if I'm unlucky and I'm just starting late, so that somewhere in the set of values that I'm collecting, I'm crossing that cache fill boundary, well, then I'm going to have to, I can't just reverse the whole list. I actually have to reverse the individual cache fill event buckets and restitch the list together. So this sounds like it makes this impractical, but in reality, in worst case scenario, you don't know where the cache fill event bucket line is. You just have to try 64 different variants, which if the solver tends to work very quickly, depending on how large that constant value is. So this is like a pretty easy thing to script up. So anyway, enough talking, enough math, enough all that. Let's do a demo. So I got that. All right, cool. So this is a web application that I quickly wrote. Put that on the side really quick. And we'll take this. This will make sense in a second. So this is a web application I quickly wrote. It's really simple. There's a login page. You can type admin, stuff like that. And you'll see I'm not logged in because I didn't put the right thing in, but I can do donut, and I could do, I think it's pastry, and log in, and now I'm logged in, and this is what the page looks like. So I'll log out really quick. So now we want to break into the admin account, right? So the way we're going to do that, is we're going to go over to the admin panel, or login panel. We're going to reset the account. We're going to say reset admin, so send a code. Now this is actually sending a code to a phone number so that it can recover the account. I actually used the Twilio API so it could send codes. Now I'm going to leave this open, and in another tab, I'm going to open up this, log in, reset, and I'm going to reset the donut account. So donut is going to send real codes to me. So I'm going to write them in as they come on my phone. So 3009150, and just refresh the page. 3238559. 3596677. And it may seem like I may have to be here forever just collecting codes, right? This is a leaded randomness. I'm losing so much information when I do this kind of stuff with Math.floor, but in reality, we're not going to need that many codes. Now, you'll notice these are a bit longer than the codes that were in the original story. Oh, not that 8's not there. But that's mostly just because, I want to ensure that our ability to predict values does not require too many codes. Otherwise, I'd be here just typing in numbers all day from my phone. So I think I'm going to put like maybe 3 more in here just so that we're really, really covered. You can always add more, but if you have too few, it can potentially produce an incorrect solution. But 1 more should do it. I think we're probably fine already, but I want to be really, really covered. All right, so now I have some of these values, right? I'm going to put that in a list. pipe it to TAC, which will actually take that list and reverse it for us, which you can see here. And then I'm going to call function. So we have, what is it, multiple, which we know the multiple here is 1,000, million, 10 million, right? So one. And now we've produced a state 0 and state 1 value. Lightning fast. And you'll notice that if I don't reverse that list, it failed to find the solution. And that's because that this is because Math.random produces the values in reverse order. So I've copied that state, the state 0 and state 1. So let's call the function one more time so we can tell it to please generate some values for us. And we're going to say generate 10 if they can. So now we can start looking for the numbers that we have, because this set will be in this set here. So 330915, 330915, there's 328, and if we go all the way back up, we'll see this is what we started with. The next value produced should be, oh, we might need to do a couple more here. Yeah, here we go. 330915, that's the value started with. Cool. There's 833441, so hopefully this should work. Reset the account. And if that worked, admin password should allow me to log in. So now I'm logged in. Now, if you don't necessarily believe that, we can set this up to do a similar experiment. So now we've set this up to use the same multiple. We'll generate some numbers here. Got to be careful not to hit that generate button twice. It'll mess up the values. And one more for good measure. All right, cool. Multiple. Oh, no, we don't need that lead value yet, but that's fine. So if that worked, it should have produced the value for us. So we're looking for 90860 or 94860 right there. The next one that we put in was this value, so we can go all the way back to 1368 right here. And now this is the next value. If I press generate, I'll get 3535437. And the next one is going to be 225455 or 2225455. There you go. And that's what was happening with the SMS codes in the Node.js. Anyway, thank you so much for watching, and hopefully you learned something cool. My socials are Donut Pointer on Twitter, Donut Pointer as well on Twitch, and you should go and learn and play Rust. Thank you very much.